Year 13, Moments of Forces, Lesson 3. So we're going to have a look at 3 examples, and in each of these questions we have a rigid rod which is on the point of tilting about a pivot. So let's take a look at the first example. Make sure you've looked at all the information on the attached PDF and you've read through all the information carefully. So let's have a look at the first question. We have a uniform plank, AB, with a weight of 120 newtons and length of 3 meters. I'm going to sketch out a slightly larger diagram here. Here's my uniform plank. One end A, one end B, and it's clearly pivoted at point C, which means there'll be a reaction force, we'll call it RC. And there's a second pivot over here at D. So there's a reaction force of the pivot pushing up on the rod, which is RD. Now, we know the weight of the plank is 120 newtons and it's uniform. So there's the weight of 120 newtons, which is at the midpoint of the rod. So this is 1.5 meters away from B and 1.5 meters away from A. We also know that the distance AC is equal to 1 meter and C to D is equal to X meters. And we are told that the reaction of the support on the plank at D has a magnitude of 80 newtons. So modelling the plank as a rod, we need to show that the distance X is equal to 0.75. So let's start off by thinking about forces. So if we remember that the system is in equilibrium, the plank is resting horizontally in equilibrium, we were told that in the question earlier on. If we balance our forces, we know that RC plus RD must equal 120, but RD is equal to 80 newtons, so RC has got to equal 40 newtons. Now, let's look at balancing moments. Now, we know the value of all of the forces in this question, so really our choice of which point to take as a pivot point for taking the moments about can be any point on the rod. Now, to make the algebra a little bit easier, I'm going to choose to take moments about point C. So let's think about the forces that we've got to take into account here. Now, RC has 0 perpendicular distance from C, so we can exclude that from our calculations. 120 newtons will have a clockwise moment, and RD will have an anti-clockwise moment, and they will balance each other out. So remember, our total clockwise moments equal our total anti-clockwise moments. So we know the 120 Newton force is acting at a point which is 1.5 meters away from A, so that means it is a distance of 0.5 meters away from C. So we have for the clockwise direction 120 multiplied by 0.5 as the moment, and for the anti-clockwise direction we have 80, which is RD, multiplied by X. An easy matter then to rearrange this and work out that X is 0.75 meters. Now, part B of the question, a rock is now placed at B and the plank is on the point of tilting about D. Now, this is the really interesting part of the question. So I'm going to sketch another diagram very quickly. So here is my uniform rod, AB. Here is the pivot at C, here is the pivot at D, and here is the rock, which is placed at point B. Let's draw in the forces, RC, RD, and remember it's forces acting on the rod, so we want the weight here, which I will just call W. So let's put in, just to finish off, the weight of the rod as well, which is 120 newtons. Now, because the plank is on the point of tilting about D, due to the weight of the rod pushing it down in one direction, what happens is that RC starts to become smaller and smaller and smaller and starts to approach a value of 0. Now this is when the plank is about to tilt, which means we're about to lose contact between the pivot at C and the plank, which means RC is starting to approach 0. At the point at which RC very definitely equals 0, that's the point at which we've lost contact. In so many situations in mechanics, we have that situation where something's about to do something. Think about limiting equilibrium, when limiting equilibrium is about to be broken in F equals mu r. It's the same sort of concept here. Because we're on the point of tilting about D, RC is going to be so close to 0 that we will take it to equal 0 in our calculations. So what can we now work out? Well, we're going to take moments again. And we are going to take moments about point B. It's easy to take moments about B. It eliminates the value of W straight away, and it's also easy to measure all of the distances from this point. So this is our pivot at B. RD will produce a clockwise moment. 120 will produce an anti-clockwise moment. So if we balance moments again, our total clockwise moments, which are represented by RD multiplied by the distance from B to D, must equal 120 multiplied by 1.5. Now, what is the distance from B to D? Well, it's this measurement over here, and we know that BD is equal to 3, take away 1, take away x, which gives us a value of 1.25. So we have RD multiplied by 1.25 equals 120 multiplied by 1.5. RD can then be worked out to be 144 newtons. If we then balance forces for the system in equilibrium vertically, we know that RD upwards must be balanced by 120 plus W, and this then allows us to work out the weight of the rock, which is 24 newtons. Right, example 2. Make sure again you read through the question really carefully before we start it together. So, information. We have a plank of wood, AB, with mass 10 kilograms and length 4 meters. So here is my plank of wood. And it's AB, it's pivoted at point A, and it's also pivoted at point C as well. Now we know some measurements. We know that the length of the piece of wood is 4 meters, and it's got a mass of 10 kilograms. We know that C to B is 0.4 meters, and we know that that means that A to C will of course be 3.6 meters. Let's draw on some forces. So there'll be a reaction force here and a reaction force here as well. We have a girl of mass 30 kilograms who stands at B with the plank in equilibrium. So at B, we can model the girl as a particle with a weight of 30g. Now we're modelling the plank as a uniform rod, which means that halfway along the rod is the centre of gravity or the centre of mass, and its mass is 10 kilograms, so that is a weight of 10g, and we know that's halfway along, so that's a distance of 2 meters. So we have got to use the fact that this is in equilibrium to find the reaction of the plank at A. So we know by balancing our forces that RA upwards plus RC upwards must equal the combination of the downwards forces, which is 40g. But we're going to need to take moments about a particular point and balance our clockwise and anti-clockwise moments if we're going to be able to take this further. Now, remember what we've talked about previously. If we take moments about point A, we can instantly eliminate RA because it has 0 perpendicular distance from point A, so it has 0 moment about A. So let's do this and let's look at the directions of the moments of each of the other forces. So A is our pivot. 10G will produce a clockwise moment about A. RC will be anti-clockwise, and 30G will also be clockwise. So remember, our total clockwise moments equal our total anti-clockwise moments. So let's work this out. So about A, we have 10G multiplied by 2 plus 30G multiplied by 4, and this is equal to, from an anti-clockwise direction, RC multiplied by, now this measurement over here has got to be 1.6, so the distance between RC and RA, or the distance between C and A, is 3.6. So from here we can calculate RC to have a value of 381.1 recurring newtons, but we wanted to find the reaction on the plank at A, so this means we need to use this equation here to calculate RA, and that equals 10.8 recurring newtons. It's interesting to note that the reaction force at A is only about 11 newtons, but the reaction force at C is close to 400 newtons. Now, why is that? That's because C is much closer to where the girl is standing on the plank, which means that RC has to be larger to counterbalance the girl and to ensure that the plank stays in equilibrium. A is a lot further, which is why the reaction force of the pivot at A is a lot less. So the girl now steps off the plank, and a boulder of mass m kilograms is placed on the plank at A. A man of mass 80 kilograms stands on the plank at B. The plank is in equilibrium and is on the point of tilting about C. We need to find the value of m, the mass of the boulder. Well, the first thing we need to do is sketch a new diagram. New situation, new diagram. So here is our plank, AB. Now the girl is no longer there. The pivot at A remains. So here's RA. And the pivot at C remains. So here is RC. And we have the weight of the rod, which was, of course, 10G. That was a distance 2 meters from A. Now let's add on the boulder, which is placed at A, which has a mass of m kilograms, so we'll give its weight there, which is mg. And at B, we have a man of mass 80 kilograms, so there's his weight, 80g. Plank is in equilibrium and it's on the point of tilting about C. Now, what does that mean? If the plank is on the point of tilting about point C, that tells us that in a minute, essentially, we're going to lose contact between the plank and the pivot at point A, which means that RA is going to effectively approach 0 as the plank is about to tilt about point C. So let's think about forces. If we balance our forces, so part B, we know that RC must equal mg downwards plus 90g, the combination of 10g and 80g. Now, what about moments? Well, we've got a number of places in which we could take moments very easily. I am going to take moments about point A again. It's very convenient. It means we eliminate RA and mg instantly. We'll be left with an equation that only contains RC, and we can substitute it into this equation here to find the value of m. So taking moments about point A. So let's have a look at the directions. 10g will produce a clockwise moment. RC will be anti-clockwise. ATG will also be clockwise. Our total clockwise moments equal our total anti-clockwise moments. So let's set up our equation. 10G multiplied by 2 plus ATG multiplied by 4 has got to be balanced by RC multiplied by 3.6. We can rearrange this to find our value of RC, which works out to be 925.5 recurring newtons. Now, as we said previously, we're now going to substitute this information into this equation here. So that tells us that 925.5 recurring equals mg plus 90g, and it's a very small piece of algebra that we need to do to work out the value of m, which is 4.4 recurring kilograms.